Something appeared in the latest images of 3i Atlas that shouldn't exist. Jets of gas and dust extending vast distances into space, appearing unusually narrow and aligned for such an active comet, not drifting, not smearing, not behaving like anything we've seen before. This is an object spinning through the darkness at tremendous speed, and yet its exhaust plumes are staying locked in place like beams of light cutting through the void. That's not how we'd normally expect comet jets to behave based on current models of rotation and outgassing. And yet there they are. Imagine holding a sparkler and spinning in circles. The light streaks into a blur, doesn't it? Now imagine that sparkler somehow keeping its flame in a straight narrow line no matter how fast you turn impossible. But that's exactly what we're watching happen with 3i Atlas, an interstellar visitor that has travelled across the galaxy to show us something that pushes the edges of our current understanding of how comets can behave. These aren't vague observations or blurry amateur photos. These are high-resolution images captured by some of the most powerful telescopes on Earth, and the scientists analysing them are using words like unprecedented, anomalous, and deeply perplexing. Some researchers describe this as the latest in a long list of anomalies, one more example of 3i Atlas behaving in ways that seem unusual compared to typical comets. And this one might be the most significant yet because it challenges something fundamental, something we thought we understood about how spinning objects behave in space. Harvard astrophysicist Avi Loeb released an analysis just days ago laying out the problem in stark terms. The rotation period was measured back in the summer. The object is tumbling through space every 16 hours. So why aren't the jets tumbling with it? Why aren't they smeared across the sky like every other rotating comet we've ever observed? We've been following 3i Atlas since it emerged from the darkness between stars, and every week brings another layer of strangeness. This isn't about wild speculation or conspiracy theories. This is about data. This is about measurements that don't add up. This is about watching something move closer to Earth and realizing that the closer it gets, the less it makes sense. And the clock is ticking. Clock is. On December 19th, this object will make its closest approach to our planet, passing within viewing range of instruments that could finally give us answers. But right now, in mid-November, we're left staring at images that show something that shouldn't be possible. Stay with me. In the next few minutes, we're going to walk through exactly what these new images reveal, why the scientific community is so unsettled, and what it means for our understanding of interstellar objects. We're going to examine the 12 anomalies one by one, explore the natural explanations that might solve this mystery, and confront the uncomfortable questions that emerge when those explanations fall short. This isn't just about one strange comet. This is about the moment we realize that the universe might still have the power to genuinely surprise us. And if you're watching this because you've been following the 3i Atlas story, if you've been waiting for the next piece of the puzzle, then drop a comment telling me what you think is happening here. Are we looking at exotic ice chemistry we don't understand? Unusual outgassing patterns driven by the object's composition? Or something else entirely? Hit that like button if this mystery has pulled you in the same way it's pulled in scientists around the world, because this is the kind of discovery that reminds us why we look up at the sky in the first place. The 12th anomaly changes everything because it's not just another strange measurement, it's a fundamental challenge to the natural comet hypothesis. And as we unpack what these November images show, you're going to see why even the most skeptical researchers are admitting that 3i Atlas is unlike anything in our catalogue of cometary observations. The rotation paradox is real, the jets are there, and the explanations we've relied on for decades suddenly feel inadequate. Let's begin with what rotation means, why it matters, and why these perfectly collimated jets are causing such profound confusion among the people whose job it is to understand how objects move through space. Every object in space rotates, asteroids tumble, comets spin, planets turn on their axes. This isn't optional physics, it's the natural result of formation processes, collisions, gravitational interactions. When something forms in the chaotic environment of a stellar system, or gets ejected into interstellar space, it carries angular momentum with it. That momentum expresses itself as rotation, and that rotation persists across unimaginable distances. 3i Atlas is no exception. Back in July and August, as this object approached the inner solar system, astronomers measured its rotation period. The data was clear. Every 16 hours, 3i Atlas completes one full rotation. It's spinning like a cosmic cartwheel, tumbling through the darkness. Now here's where the problem begins. When a comet rotates, and that comet is actively outgassing, releasing jets of material from its surface as ice turns to vapor under the sun's heat. Those jets rotate with it. Think of it like this. Imagine you're standing in the middle of a field with a garden hose, water spraying out in a steady stream. Now start spinning. The water doesn't stay in one direction, does it? It arcs across the sky, creating a spiral pattern as you turn. The faster you spin, the more the water spreads out. The same principle applies to comets. As the nucleus rotates, the jets of gas and dust should sweep across space, creating a smeared fan-like pattern. We've observed this behaviour hundreds of times with comets in our own solar system. It's textbook cometary physics. But 3i Atlas isn't following the textbook. The images show jets that are narrow, collimated, and directionally stable. They're not smeared. They're not fanned out. They're pointing in specific directions, maintaining their structure across distances that should absolutely blur them into diffuse clouds. Avi Loeb's analysis describes them as appearing locked in orientation, as if the rotation isn't affecting them at all. How is that possible? How does a spinning object produce non-spinning exhaust? Let's think about what we're actually seeing. These jets extend outward across enormous distances in space, far enough that even modest rotation should noticeably smear them. That's roughly 3 times the distance from the Earth to the Moon. At that scale, even the slightest rotation of the source should smear them into broad arcs. Imagine pointing a laser pointer at a distant wall while slowly turning your wrist. Even a tiny movement creates a long streak of light on that wall. Now imagine the light somehow staying in one spot despite your hand moving. That's the puzzle. That's the paradox. The source is rotating, but the output looks static. There are only a few ways this could happen, and none of them fit comfortably into our understanding of natural comets. The first possibility is that the rotation has stopped. Maybe something happened, a collision, a gravitational interaction, some internal structural change that halted the spin. But there's a problem with that explanation. Objects in space don't just stop rotating. Angular momentum is conserved. For 3i Atlas to go from a measured 16-hour rotation period to zero rotation would require a massive transfer of energy, something dramatic enough to be visible in the data. There's no evidence of such an event. The object didn't shed significant mass. It didn't fragment into pieces that carried away the angular momentum. The rotation was there in the summer, and there's no physical mechanism that would have erased it by November. The second possibility is that the jets are coming from specific locations on the surface that happen to align with the rotation axis. Think of the poles of a spinning globe. If you placed a fountain at the North Pole and spun the globe, the water would shoot straight up without sweeping across the sky because it's positioned on the axis of rotation. This is actually a plausible explanation, and it's one that scientists are seriously considering. But it has complications. For this to work, the active regions producing the jets would need to be located almost exactly at the rotational poles, and they'd need to be producing enormous amounts of material from those very specific spots. That's unusual. Most comets have multiple active regions scattered across their surfaces, not concentrated at the poles, and even if the jets were polar, we'd expect to see some wobble, some precession, some indication that the axis itself is shifting. The images don't show that. The third possibility is the one that's causing the most discussion, and it's the one that makes people uncomfortable. What if the jets aren't passive outgassing? What if they're being actively collimated by some process we don't understand? Not necessarily artificial, let's be clear about that, but something beyond simple ice sublimation. Maybe there are subsurface cavities that channel the gas into narrow beams. Maybe there are magnetic fields at play, though comets aren't supposed to have magnetic fields strong enough for that. Maybe the internal structure of 3i Atlas is so unusual, so different from normal comets, that it's producing behaviour we've never encountered before. This is where the rotation paradox deepens into something more profound. It's not just about the jets, it's about what the jets imply about the object itself. If 3i Atlas is behaving in ways that defy our models, then maybe those models are incomplete. Maybe interstellar objects, forged in alien stellar systems under conditions we can't replicate, don't follow the same rules as the comets born in our own solar neighbourhood. Or maybe, and this is the thought that lingers at the edge of every analysis, we're looking at something that isn't entirely natural. But before we go down that path, we need to understand the full scope of what makes this object strange. The collimated jets are just one piece of a much larger puzzle. They're the latest reported anomaly, but they don't exist in isolation. To truly grasp why scientists are so unsettled by what they're seeing, we need to look at the complete pattern of unlikely and unusual behaviours that 3i Atlas has presented since the moment it entered our detection range. Because when you stack these anomalies together, when you see them as a collective phenomenon rather than isolated quirks, the picture becomes far more unsettling than any single measurement could ever be. One anomaly is interesting. 2 anomalies are curious. 3 might be coincidence. But when enough unusual features start stacking up, they begin to look less like coincidence and more like a pattern that demands explanation, and patterns demand explanation. What we're seeing with 3i Atlas isn't a single strange measurement that could be dismissed as instrument error or observational fluke. It's a systematic deviation from what we'd normally expect based on our experience with solar system comets so far. Let's walk through them, one by one, because the power of this mystery isn't in any individual oddity. It's in how many of them seem to line up at once. The first anomaly is the trajectory. 3. I-Atlas didn't just drift into our solar system on a lazy hyperbolic path. It came in steep and fast with an orbital inclination that marked it immediately as interstellar. But what caught attention was the precision of that trajectory, arriving from a specific region of sky that doesn't align with any obvious stellar nursery or nearby star system. It's not coming from the direction of any catalogued stellar neighbourhood. It's coming from the void. The second anomaly is the brightness profile. When 3i Atlas first appeared, it brightened far faster than models predicted. This happens when comets approach the Sun and their ices begin to vaporize, but the rate of brightening was steeper than expected. Then it did something even stranger. It dimmed dramatically after perihelion, the point of closest approach to the Sun, before brightening again. That kind of fluctuation suggests changes in activity level that don't match typical cometary outgassing patterns. The third anomaly is the non-gravitational acceleration. This is where things get technical but critically important. When comets outgas, the jets of material push against the nucleus like tiny rocket engines, causing the object to accelerate slightly in directions that aren't purely gravitational. This is normal. What's not normal is the magnitude and direction of 3i Atlas's non-gravitational acceleration. The measurements show a force component that's larger than expected, and oriented in ways that don't align cleanly with solar radiation pressure or simple outgassing models. The fourth anomaly is the lack of a visible coma. Most active comets develop a fuzzy cloud of gas and dust around their nucleus called a coma. It's the hallmark of cometary activity. 3i Atlas has jets. Clear, defined jets. But its coma is far less prominent than you'd expect given the intensity of those jets. It's as if the material is being channeled into narrow streams rather than diffusing into a broad cloud. That's unusual. The fifth anomaly is the anti-tail. This is a strange optical phenomenon where cometary material appears to point toward the Sun rather than away from it. Anti-tails happen under specific geometric conditions, but the one observed with 3i Atlas was particularly pronounced and persisted longer than typical anti-tail features. It suggests something about the particle size distribution or ejection velocities that doesn't fit standard models. The sixth anomaly is the spectrum. When astronomers analysed the light reflected and emitted by 3i Atlas, they found spectral signatures that don't match the usual suspects. The composition appears different from solar system comets, potentially richer in certain volatiles, potentially containing materials that formed under different temperature and pressure conditions. It's the fingerprint of an alien chemistry, literally shaped by a different star. The seventh anomaly is the outburst timing. 3i Atlas experienced multiple sudden increases in brightness, outbursts where activity spiked dramatically before settling back down. These outbursts didn't correlate cleanly with distance from the Sun. Some happened when you'd expect them, but others occurred at times and distances that don't fit the thermal models. It's as if the object has internal triggers that aren't purely temperature-driven. The eighth anomaly is the shape inference. While we don't have resolved images of the nucleus itself, the light curve data, how brightness varies over time, suggests an elongated shape, possibly highly irregular. Some analyses hint at an aspect ratio that's more extreme than typical comets, raising comparisons to 1I/Oumuamua, the first confirmed interstellar visitor, which had a similarly unusual elongation. The ninth anomaly is the jet morphology. Even before the November images revealed the collimation problem, earlier observations showed that the jets had unusual structures, narrow, persistent, and emerging from discrete points rather than broad active regions. The geometry didn't look like the chaotic, messy outgassing seen on most comets. It looked controlled. The 10th anomaly is the dust-to-gas ratio measurements suggest that 3I Atlas is producing less dust, relative to gas, than expected. This matters because dust is what makes comets visible. It reflects sunlight and creates those beautiful tails we see in the sky. A low dust-to-gas ratio means the object is releasing a lot of vapor, but not much solid material that could indicate a composition dominated by highly volatile ices, or it could mean something about how the material is being released from the surface. The 11th anomaly is the post-perihelion behavior. After passing closest to the Sun in late October, 3I Atlas should have begun a steady decline in activity as it moved away and cooled down. Instead, it remained active at levels higher than predicted, and some observations suggested the activity might have even increased temporarily. That kind of sustained or resurgent activity is hard to explain with passive solar heating alone. And now, the 12th anomaly, the one we've been discussing, the collimated, rotationally stable jets that shouldn't exist given the measured rotation period. This is the latest piece, the one that arrived in November, and it's the one that ties all the others together into something genuinely perplexing. Here's what you need to understand. Each of these anomalies, taken individually, could potentially be explained. Unusual trajectory. Maybe it got gravitationally perturbed by something we didn't detect. Strange brightness curve. Maybe unusual ice distribution, non-gravitational acceleration, maybe asymmetric outgassing. We can construct explanations for individual oddities, but when you stack 12 of them together, the odds of a single natural comet showing this many unusual features at once start to look very small. At least if we rely only on the templates built from comets in our own solar system. Avi Loeb has been making this argument explicitly. He's not claiming proof of anything extraordinary. What he's saying is that the cumulative statistical weight of these anomalies pushes 3I Atlas into a category of its own. It's not like 1I Oumuamua, which showed a couple of strange behaviours but was largely inactive. It's not like 2I Borisov, which was a fairly normal-looking comet that just happened to come from outside the solar system. 3I Atlas is active, anomalous, and persistently weird across multiple independent observational categories. This is where the investigation becomes uncomfortable, because the natural instinct is to find a unifying explanation, one underlying cause that accounts for all the strangeness. Maybe it's composition. Maybe interstellar comets are just fundamentally different because they formed around stars with different metallicities or in molecular clouds with exotic chemistry. Maybe the conditions out there in the galaxy produce objects that don't fit our solar system. Derived templates. That would be the conservative explanation, and it's entirely possible. But what if the unifying explanation isn't just exotic composition? What if there's something about the structure or behaviour of 3I Atlas that's fundamentally different from passive cometary bodies? That's the question hanging in the air as we move toward December. That's the tension driving the scientific debate. And that's why the next section matters, because we need to seriously examine the natural explanations, give them their full due, and see whether they can actually account for what we're observing. Science works by elimination. You start with the simplest, most natural explanation and test it against the data. If it holds, you're done. If it doesn't, you move to the next possibility. The problem with 3I Atlas is that we're running out of simple explanations. But let's walk through them honestly, because understanding why the natural explanation struggle is just as important as acknowledging that they exist. The most straightforward explanation for the collimated jets is polar outgassing. If the active regions producing the jets are located at or very near the rotational poles of the object, then as it spins, those jets would point in a relatively stable direction. Think of the Earth spinning on its axis. The North Pole always points toward Polaris, even as the planet rotates. If 3I Atlas has concentrated ice deposits at its poles, and if solar heating is triggering outgassing specifically from those regions, then the jets could maintain their directionality despite the 16-hour rotation. This is plausible. It fits within known cometary behaviour. We've seen polar jets before on other comets, though usually not in isolation. Most comets have multiple active regions scattered across their surfaces, but let's say 3I Atlas is an exception. Let's say its particular formation history left it with ice concentrated at the poles and a relatively inactive equatorial region that would explain the jet collimation, but it doesn't explain the intensity. Polar regions receive less solar radiation per unit area than equatorial regions because of the angle of sunlight. To produce jets as prominent as what we're seeing would require extremely volatile ices, materials that sublimate very easily even under modest heating. That's not impossible, but it's adding another layer of specialness to the explanation. The second natural explanation involves topographical effects. Maybe the surface of 3I Atlas isn't smooth. Maybe it has deep valleys, craters, or fissures that channel out gassing into narrow beams. Imagine a canyon on the surface with ice deposits at the bottom. As the sun heats that ice, the vapor rises through the canyon walls, which act like nozzles, focusing the gas into a collimated stream. We know that country surfaces are complex, full of pits and fractures. This kind of topographical focusing could create the narrow jets we're observing. But there's a problem. For this to work across multiple jets pointing in different directions, you'd need multiple topographical features with very specific geometries, all producing collimated outgassing simultaneously. And you'd need those features to be positioned such that they maintain their orientation relative to the viewer despite the object's rotation. That requires a very particular configuration. Not impossible, but increasingly unlikely as you add more constraints. The third explanation is fragmentation. Maybe what we're seeing aren't jets from the main nucleus at all, but trails of debris from smaller fragments that have broken off. When comets fragment, the pieces can leave behind trails of dust and gas that appear as linear features in images. If 3I Atlas is actively breaking apart, those fragment trails could create the appearance of collimated jets. This would also explain some of the brightness fluctuations and the unusual dust-togas ratios. Recent reports suggest that 3I Atlas may indeed be fragmenting. Observations in mid-November indicate possible breakup activity. If confirmed, this would be significant. Fragmentation is a natural process, especially for interstellar objects experiencing the thermal stress of passing close to a star for the first time in potentially millions of years. The ices holding the object together could be sublimating from the interior, creating internal pressure that causes structural failure. That's a perfectly reasonable scenario, but here's the complication. If the jets are fragment trails, they should be evolving rapidly. Fragments move away from the parent body over time, and their trails spread out and fade. The jets of 3I Atlas have been observed over weeks, maintaining their structure and intensity. The persistence is hard to reconcile with transient fragmentation events. You'd need ongoing, continuous breakup to sustain the jet features, and that level of activity would likely produce other observable signatures, like a rapidly expanding debris cloud, that aren't clearly evident in the data. The fourth explanation is radiation pressure and magnetic effects. Maybe the jets are being collimated by forces beyond simple gas dynamics. Solar radiation pressure can push dust grains in specific directions. If there's some unusual interaction between the solar wind, the comet's plasma environment, and the ejected particles, maybe that interaction is channeling the material into narrow streams. Magnetic fields, if present, could also shape the flow of ionized gas. This is where we enter speculative territory. Comets do interact with the solar wind, and they do develop plasma tails shaped by magnetic fields. But those fields are external. They're imposed by the sun, not generated by the comet itself. For internal magnetic fields strong enough to collimate jets, you'd need something unusual in the composition or structure of 3I Atlas. Maybe it has metallic components, remnants of a disrupted planetary core from its home system. Maybe it formed in an environment with strong magnetic fields that organized its structure. These aren't mainstream ideas, but they're not impossible. The honest answer is that we don't know yet. Each of these natural explanations has merit, and each has gaps. The polar outgassing hypothesis requires specific ice distributions and extreme volatility. The topographical focusing hypothesis requires complex surface geometry, aligned in improbable ways. The fragmentation hypothesis requires sustained breakup activity that doesn't fully match the observational timeline. The radiation pressure hypothesis requires mechanisms we haven't directly detected. What's important to understand is that science isn't stuck. There are ongoing observations, new images being captured, spectroscopic analyses being refined. The December 19th closest approach will bring 3I Atlas within optimal viewing range for some of the world's most powerful instruments. We'll get better data on the rotation state, the jet structure, the composition, and possibly even the surface features. That data will constrain these hypotheses, it will rule some out and strengthen others. For now, the mainstream view in the scientific community is that 3I Atlas is a natural interstellar comet, with unusual but explainable behaviour, not an artificial object. But right now, in mid-November, we're in a state of genuine uncertainty. And that uncertainty is what makes the next part of this conversation necessary, because when natural explanations strain under the weight of accumulated anomalies, when each hypothesis requires adding more and more special conditions, science demands that we at least consider alternatives, even uncomfortable ones. There's a hypothesis that no one wants to say out loud, but it's there, hovering at the edge of every conversation about 3I Atlas. What if it's not entirely natural? Not necessarily alien technology, let's be absolutely clear about that, but something that blurs the line between natural object and designed artifact in ways we're not equipped to categorize yet. Avi Loeb has proposed a framework for evaluating interstellar objects called the Loeb scale. Similar in concept to scales used for assessing asteroid impact risks or potential biosignatures. It ranks objects based on how many anomalies they exhibit, and how difficult those anomalies are to explain through conventional astrophysics. On this scale, 3I Atlas currently sits in a category that Loeb describes as warranting serious investigation beyond standard cometry models. He's not declaring it artificial, he's saying the data justifies keeping that possibility in the investigative framework rather than dismissing it reflexively. A highly speculative idea sometimes discussed on the fringe is the technological thruster hypothesis, which tries to address the collimated jets directly. If the jets are being actively controlled, if they're producing thrust in specific directions rather than passively venting in all directions, that would explain the lack of smearing. It would explain the non-gravitational acceleration. It would explain the sustained activity and the unusual geometry. But it requires accepting that we're looking at engineering rather than geology. Is that likely? Statistically, astronomers consider it extremely unlikely compared to natural explanations. The universe is vast, and interstellar travel is extraordinarily difficult. The odds of an alien probe happening to pass through our solar system at the exact moment we have the technology to detect it are vanishingly small, but they're not zero. And when you're faced with data that doesn't fit natural models, the scientific method requires considering all hypotheses that fit the data, even the uncomfortable ones. What would change the ranking on the Loeb scale? What would push 3I Atlas from intriguing anomaly to genuine technosignature candidate? Evidence of directional control would be the big one. If the object changes course in ways that can't be explained by gravitational interactions or outgassing, that's significant. If the jets pulse in patterns rather than continuous flows, that's significant. If spectroscopy reveals materials that shouldn't exist in natural formation environments, that's significant. None of those have been definitively observed yet, but December 19th offers the opportunity to look. On that date, 3I Atlas will pass closest to Earth. Not dangerously close, but close enough that our best instruments will have optimal viewing angles and signal strength. Radio telescopes will be listening for any electromagnetic emissions. Optical telescopes will be capturing high-resolution images of the jet structures. Spectrographs will be analysing the chemical signatures in unprecedented detail. If there's something unusual about this object beyond what we've already seen, this is the moment we'll detect it. And that's where this story rests for now. Not with answers, but with anticipation. We're watching something genuinely mysterious, something that doesn't fit neatly into our categories, and we're doing it in real time. There isn't ancient history pieced together from fossils and geological records. This is happening now, unfolding across our telescopes and data streams as an interstellar visitor makes its closest approach to our world. Maybe the December observations will resolve everything. Maybe we'll get images showing clear fragmentation that explains the jets. Maybe we'll detect rotation in the jet orientations that earlier observations missed. Maybe the spectroscopy will reveal a composition so exotic that it naturally produces all the strange behaviours we've been puzzling over. That would be satisfying. That would close the loop. Or maybe the mystery will deepen. Maybe we'll find more anomalies. Maybe the data will push us further into the uncomfortable space where natural explanations feel insufficient and extraordinary hypotheses start demanding serious consideration. That wouldn't give us closure, but it would give us something perhaps more valuable. Proof that the universe can still surprise us, still show us phenomena that challenge our models and force us to expand our thinking. What we're witnessing with 3I Atlas is science at its most honest. There are questions without answers, There is data that doesn't fit. There are competing hypotheses, none of them perfect, all of them grasping toward truth. This is how discovery works, not with sudden revelations and definitive pronouncements, but with incremental observations, rigorous analysis, and the humility to admit when something doesn't make sense yet. The 12th anomaly, those impossibly collimated jets frozen in space despite a 16-hour rotation, is the latest chapter in a story that's far from finished. As we move toward the closest approach, as more telescopes turn toward this distant visitor, we're all part of the investigation. Every view, every comment, every shared conversation about what this object might be contributes to the collective attention that keeps science-funded and curious minds engaged. So stay curious, stay skeptical, demand evidence, but remain open to the possibility that evidence might point toward conclusions we didn't expect. Because whether 3, I-Atlas turns out to be an exotic comet with unusual chemistry or something far stranger, it's already accomplished something remarkable. It's reminded us that the space between stars isn't empty void. It's filled with travellers, with objects shaped by alien suns and carrying stories written in compositions we're only beginning to learn how to read. And this traveller, tumbling through our neighbourhood with its impossible jets, is telling us a story we don't fully understand yet. That's not a failure of science, that's an invitation to discover.